Hello everyone, we're going to be solving one more problem on 2D rigid body equilibrium, and in this problem we will see the effect or the use of having a two-force member in order to support the given rigid body. Alright, so this is also one more problem on 2D rigid body equilibrium. So 2D rigid body equilibrium. And we're going to see the effects of two-force member. These are typically also rigid bodies, and they are mostly used for structural support. They're used for propping up structures or for buttressing structures. So here is a problem that we're going to be solving today. There are two rigid bodies that are connected in the following fashion. So here is the first one. I have a long horizontal bar. We will call this as A, B, D. It's pinned at one of its ends. So there is a pin at the point A. Okay, so here is a pin. Obviously, you can see that this rigid body is not going to be supported if this is the way it is. So this means that there is another rigid body that is pinned at a different point along the wall and connected to this body here. So I'm just going to draw a straight line from here just to show the place where the other rigid body is going to start from. So I'm going to have one more rigid body which is going to come all the way, and this will be pinned together at the rigid body that I have drawn in blue. Alright, so there is going to be a pin here. So these two are pinned together at that particular point. There is one more pin here on this rigid body which is connecting it to the wall as shown. Alright, and then there are some applied forces of course which are acting on these rigid bodies. So here is one of the rigid bodies. This is actually going to be our two-force member here, and then the other one which is going to be marked in blue as well as in the fluorescent color. There are some applied forces acting on it, and here are the applied forces. So I have a force of 200 newtons which is acting at the end of the beam, the horizontal beam. So this is a force of 200 newtons in magnitude. Then I'm going to have a couple moment which is acting on the horizontal bar. This has a magnitude of 300 Newton meters, and it is drawn in the clockwise direction. As you can see, the fingers of my right hand, if I curl it along the direction of the couple moment, it is pointing in the clockwise sense. Then I have one more force of magnitude 150 newtons which is acting at an angle of 45 degrees to the vertical or to the horizontal. 45 degrees is the perpendicular, is a bisector of the 90 degree angle here. So this angle here is 45 degrees. Then we have some dimensions for this problem. Dimensions are going to be marked as follows. So first of all, this is the point A. This we're going to call as C. Here is B, where the two bodies are pinned together, and then this is D. Alright, so dimensions all the way from point A to where this force is acting is 2 meters. Then all the way from the point C to where the point B is also it's 4 meters. It's twice that distance. So this is 4 meters, and then this final distance here is going to be 2 meters, and then the distance from point A to point C vertically is given to us as 3 meters. Alright, so all the dimensions are given to us. We need to find support reactions at the point A and at the point C. Alright, so find support reactions. At the point A and C, and we are told that the bar BC is pinned to the bar ABD at the point B. Okay, so bar BC is pinned to the bar ABD at point B. Alright, so here is the problem once again. I have a horizontal bar ABD, and then that is pinned at the point A. Then I have this support bar here, which is bar BC. That's actually going to be the two-force member here. We will see why that is the case. This is pinned at the point C to a fixed wall, and then both the bars ABD and the bar BC are pinned together at the point B. There is no support at the point D because it will become redundant if you add an extra support at D. There are a series of forces and couple moments acting on the bar ABD only, as you can see in the figure. A force of 200 newtons in magnitude. I have a couple moment of 300 newton meters clockwise. Then I have a force of 150 newtons in magnitude, which is at an angle of 45 degrees with respect to the vertical or the horizontal. Distances from point A to where this force is acting is 2 meters as given here. Distance from point A to point B, which is the same as that from C to B, is 4 meters. Distance from point B to point D on this bar ABD is given as 2 meters here. And the height from the point A to the point C is given as 3 meters vertically. Which means that in reality we can construct a slope triangle for this bar BC, and the slope triangle will have sides of 3, 4 and 5. We will make use of this idea very soon. What are the things we need to find? We need to find the reactions at the points A and C, which are pinned together at the walls respectively. And then we are also told that the bar BC is pinned to the bar ABD at the point B. Alright. So that being said, our first step is to actually draw the free body diagrams of the rigid bodies of interest. We will come back to this problem statement once again. If you look at the problem statement here, you see that there are two rigid bodies. There is this bar ABD and then there is this bar BC, which means that I have to draw two free body diagrams. And you see that it is pinned at the point A, pinned at the point C. There is a pin joining the bar ABD and the bar BC. So these are the things I need to keep in mind. And from this problem you basically see that the height here is not given to us, neither is the width or the thickness of this bar BC, which means that it does not make a difference to us. We could as well draw these as horizontal lines and just an angular straight line without any thickness to that particular line, which is what I'm going to employ here. So I'm going to have first of all two free body diagrams. The bar ABD, I'm just going to draw it as a horizontal bar here. So this is the bar ABD. We don't really care what its thickness is. Then I'm going to have the bar BC. Right, so here is the bar BC. And what we were told in the previous problem is that there was in the previous page is that there is a pin at the point A, which means that if this is the bar ABD, the horizontal bar ABD, then I start off by drawing the pin reactions at the point A. And we know from what we've done in class that there are two pin reactions typically in 2D along the directions of constraints. So this is going to be AX, and then this we're going to call as AY. Then I have this force of 150 newtons right here. This force of 150 newtons, I can split it into a horizontal and a vertical component, and 150 times cosine 45 is 106.1 Newton, and sine 45 is the same as cosine 45. So I'm going to take this force, split it into two components here. Okay, so there's going to be one, so I'm going to draw the applied forces in a different color, so probably in the black color. So there's going to be first of all 106.1 Newton component vertically, and then a horizontal component as well, 106.1 Newton force. As you can see, these are the components of the 150 Newton force at an angle of 45 degrees. I have a couple more here. There is a 200 Newton force which is acting vertically down, and then I have this couple moment which I also have to draw. This is acting clockwise, and this is of magnitude 300 Newton meters. Now you see I have not drawn anything at the point B. So here is the point B, I have not drawn anything at that particular point at this point in time. I'm just going to call it as the point B. Here is the point A, of course. You can call this as the point A if you wish. What I'm going to do next is I'm going to directly look at the bar BC, and I'm going to draw the free body diagram of that bar. So I'm just going to take this bar, I'm going to rip it away from everything that holds it in place, and you see here that there is a pin at C, there is a pin at B. And whenever I have a pin, I'm going to have two support reactions, one along the horizontal and one along the vertical, which means that these are the directions of constraint. The pin prevents the bar from moving along these directions, horizontally and vertically. And so I'm going to draw the free body diagram of the bar BC right here. So for the bar BC, we're going to have a CX and a CY. I'm choosing arbitrary directions. I'm going to have a BX and a BY. Alright, so these are completely arbitrarily chosen directions. I have some dimensions for this as well, 3 meters, 4 meters and so on. So let's look at the dimensions here. This is going to be 3 meters, and this is going to be 4 meters, and if you want, you can draw this as a nice slope triangle 3, 4 and 5. Alright, so that being said, now we are ready to draw the forces at the point B on this bar ABD. You see that this point B on the bar BC, so this is the bar BC here. This is the free body diagram of BC. This is the free body diagram of A, B, D. What is important here is that at the point B, the bar BC and the bar ABD are connected together by pin, which means that if I am drawing pin reactions BY and BX on the bar BC at the point B, according to Newton's third law, there should be a set of equal and opposite forces at the point B on the bar ABD. And so I'm going to mark them in equal and opposite directions, which means that if BY was pointing down here, BY is going to be pointing up there, and I'm going to have a BX pointing in the opposite direction, as you can see, to the BX that is drawn here. So these will be equal and opposite. So the set of forces BX and BY on the bar BC at the point B will be equal and opposite to the BX and the BY on the bar ABD at the point B. This is a really crucial point. The important thing is this: if you have already accounted for the directionality changes by drawing BY and BY to be in the equal and opposite directions, we don't need to worry about their magnitudes. Whatever we get is going to be the magnitude. We don't need to particularly go ahead and say, okay, if BY is 100 newtons after solving the problem, the BY here is a minus 100 newtons. It is not necessary to do that. I'm still not done. I need dimensions for this problem. So from point A to all the way here is going to be 2 meters. This distance here, the remainder of the distance is 2 meters, and all the way from here to the end of the bar, which is the point D, is also 2 meters. Alright, so all the dimensions are in place. This is the free body diagram of the bar BC. This is the free body diagram of the bar ABD. Excuse me. Now I'm going to look at the free body diagram of the bar BC only. So I'm going to redraw the free body diagram, and then we will dissect this, and we will see what happens once we do that. There will be some useful information that we can perhaps obtain. Alright, so look at the bar BC. I have the bar drawn at an angle, and then I have the reaction forces CX and CY and BX and BY. So this is CX, this is CY, and this is BX, BY, drawn as shown in the previous page. I have some dimensions as well. Alright, 3 meters and 4 meters. Now look at this. We know that every rigid body that we consider in this particular class is going to be in a state of equilibrium, which means that I can employ the forces of force balance and moment balance or the equations of equilibrium on the bar BC. If I do that, if I set up a coordinate system, if I say that okay, this is x and this is y, and counterclockwise rotations are taken as positive, I'm going to start off by summing forces in the x direction, which essentially tells me that Cx is equal to Bx. There is no surprise here. These are the only two forces along the horizontal direction, then they have to be equal and opposite. If I do similar stuff along the y-axis, I will find out that Cy is the same as By. Once again, no surprise, those are the only two forces in the y direction on the bar BC. Then I go to the moment balance equation. I'm going to choose the moment at the point C. I'm going to set that equal to 0, and I'm going to say counterclockwise rotations are treated as positive. And if that is the case, look at this. Bx, right hand rule. If I perform the right hand rule, the palm faces the point C, curl my fingers, produces a moment in the upward direction, so that's a distance of 3 meters from the point C. So I'm going to have Bx times 3, and then I'm going to have By and a distance of 4 meters, and it produces a clockwise rotation, which means according to my sign convention that's negative. So this is going to be minus By times 4 is equal to 0, which means that 3 times Bx is equal to 4 times By, or Bx by By is equal to 4 by 3. And you see here that the value of the force Bx and the force By, they are equal to a ratio. And this obviously means that Bx and By should be components of the same force. And this ratio is also good because I can write 4 by 3 to be equivalent to 4 by 5 by 3 by 5. And if I say that there is a resultant force of Bx and By, if the resultant of Bx and By is a force FBC, right? You see, if I can mark that force right on there, so if I call that force as FBC, then I can say that this is FBC on the numerator, FBC on the denominator, which means that Bx is actually going to be equal to 4/5 FBC, By is going to be equal to 3/5 FBC. Once again, look at the basic idea. Cx is equal to Bx, Cy is equal to By. And then I perform a moment balance about the point C. We might as well choose the point B, that makes no difference to us. If I choose the point C for the moment balance, I get Bx divided by By as a ratio of 4 by 3. If two forces are in a particular ratio, then it is quite obvious that they're going to be components of a given resultant force because they will complete a right angle triangle 4, 3 and 5. And so this means that this ratio of 4 by 3 can be split into two parts, a 4/5 FBC, a 3/5 FBC, where this FBC is a resultant of the force Bx and By. And you see, since Bx and By are the same as Cx and Cy, the resultant of Cx and Cy should also be the same as the resultant of Bx and By, and as a result, I'm going to have an FBC here as well. And you see that instead of drawing the force Cx and Cy, instead of drawing the force Bx and By, I can just draw the force FBC, and I'll be done with this problem. I don't need to worry about Bx and By and so on, because I know that Bx and By are obviously components of FBC. Right, so with that being the case, look at this here. We're now going to draw the free body diagram of BC once again. So here is a bar BC. And now instead of drawing Bx and By, Cx and Cy, I'm going to draw a force FBC. This is a force FBC. And what's the big idea? You see that this is the point C and this is the point B. I have the slope triangle. We previously wrote this down. This is 3, this is 4 and this is 5. And if I want, I can call this force, which is going to be 4/5 FBC, as equal to Bx. And I can call this force here, which is going to be 3/5 FBC, this is equal to actually By, and I can do the same thing here. I can say that 3/5 FBC here is going to be the same as CY, and the 4/5 FBC here is the same as CX, because I know that CX is the same as BX, CY is the same as BY, and I'm pretty much done. And so this means that BC is a 2-force member. What does that mean? That means that there are forces acting at only 2 points on this body here. You see that there are forces acting at the point C, there are forces acting at the point B, which means that there are forces acting at only 2 points on the body. So this means that forces act at only 2 points on the body. Such a body is a 2-force member. Right, so this is a very crucial thing. So once again, from the previous page, we said that okay, let us focus on the free body diagram of BC only. We split the forces into BX and BY, forces into CX and CY. These are the pin reactions. They prevent translation along the X and the Y. You perform force balance, you perform moment balance, and you find out that okay, BX to BY is a ratio of 4/3, which means that I can probably complete a right angle triangle side with 4, 3 and 5 as the sides, 5 being the hypotenuse. And the ratio of 4/3, I can write it as a ratio of 4/5 FBC, 3/5 FBC, where this force FBC is nothing but the resultant of BX and BY. And you can see that BX square, BY square is actually FBC square, and this is something we can write down here as well. BX square, BY square is FBC square, which implies that CX square, CY square is also FBC square. And so once I have these forces as FBC, I can basically say that okay, I don't need to draw the forces BX and BY at all. I can just draw only the forces FBC. And you see that since I have identified this as a 2-force member, the basic idea is that there are forces acting at only 2 points on this particular body. So what's the upshot of this? What's the upshot of identifying a 2-force member? And here is the idea. If I know that a body is a 2-force member, then I end up with the following simplifications. So if we find that a body is a 2-force body or a 2-force member, then first thing, forces act at only 2 points on the body. Second thing, because of this particular fact, and you can see that this is what happened in the previous page as well, we had forces acting at only 2 points in the body, and so essentially I can say that the forces at these 2 points are equal. FBC is equal to FBC. They are opposite in direction. You see that this is pointing this way, this is pointing the other way, and the most important thing, they are along the line joining the 2 points, which means that they are basically collinear. If I join the point B and the point C, I get the force FBC, which is joining these 2 points. It's along that particular line, so that's the line of action of the force. They're equal in magnitude and opposite in direction, right? So which means that these forces are the forces at the 2 points are equal in magnitude they are opposite in direction and they share the same line of action. How do you obtain that line of action? By basically joining the 2 points. line of action by joining the 2 points in a straight line. Right, so this is really crucial. If we find out that a body is a two-force member, the most important thing is this: I don't need to perform any equation, equilibrium, balance, and so on and so forth. I don't need to perform force balance. I don't need to perform moment balance. As soon as I see that a rigid body has forces at only 2 points on that body, then such a body is a two-force member. If it's a two-force member, then what's the big deal? The forces at the 2 points are equal in magnitude. They are opposite in direction, and then they share the same line of action, which means that they are collinear. And the important thing is that their line of action is obtained by joining the 2 points on the body on which the forces are acting by a straight line, by a smooth straight line. So with this being said, the same problem could have been given in the following form. You see, these are all examples of two-force members. For example, the problem that we had at the beginning. So this was the problem we had at the beginning. I'm not going to draw the loads acting on the body. I'm just going to draw only the pins and the other rigid body. So this was the problem that was given to us. Right. So this was a two-force member. Because we see that there are forces at this point here, and then there are forces at that point there, which means that forces at only 2 points on this body. The rest of the applied loads are acting on the other rigid body only. They are not acting on this body. If there is any other force acting on this body apart from the forces at these 2 points, then that's no longer a two-force member. Then we are done for. We have to perform the equations of equilibrium, force balance, and moment balance. The same problem can be cast in the following form. I can have a pin here. Now instead of a straight bar, I could have something that is curved. It makes no difference to us whether it is curved or straight. It performs the same function. Now this is also a two-force member. And the idea is that I can, and they're pinned together here, I can take this body here, I can draw this in the following form, whatever that form is, and then I know that since there are forces acting at only, let's call this as C, let's call this as B, so C and then B, all I have to do is just join a straight line and connect these 2 points, and I know that the force is going to be along that line, and so this is going to be FBC, and this is also going to be FBC. This is basically the same as that. If I take that rigid body, I know that if this is C, this is B, then I know the force has to be acting along that particular line here. So it does not make a difference to us whether the body is curved or straight. As soon as I recognize that there are forces acting at only 2 points in the body, it automatically becomes a two-force member for us. And the bodies need not be just straight lines. They could be in an L shape, they could be in a V shape. It does not make a difference to us as long as there are forces at only 2 points in the body. They are all two-force members. Alright, so since that is the case for us, I'm now going to redraw the free body diagrams of ABD, knowing that I have recalibrated the free body diagram of BC. So you see, if I look at BC, this was BC, and then there were forces at the point C and at the point B. So the force here was, so this was C, this was B, so this was FBC, and I know that this force was also FBC. Slope triangle was 3, 4 and 5. Now there is no sacred reason for choosing FBC to be pointing this way. I could have easily chosen FBC to be pointing the other way also. That is perfectly fine, because at the beginning of the problem I don't know what the direction of the forces are. Are they into or out? So this is also a perfectly valid choice for FBC, but the thing to keep in mind is that whether I do this choice or whether I take that choice, the forces have to be equal in magnitude, they have to be opposite in direction, and they have to be along the same line of action. As you can see here, they are along the same line of action in this case. They are along the same line of action in this case as well. Right, so I'm going to choose this one here, but this is also equally fine. What will happen is that if you chose it the wrong way, then you might just get FBC to be a negative number, which is perfectly fine, because at the beginning of the problem I did not know what the value of FBC was to start off with. Now, with that being the case, I'm going to draw the free body diagram of ABD. Here is ABD. We will go back and look at this again in a minute or two. So on ABD, if you looked at the previous page where we do the free body diagram, I'm going to have an AX and an AY. This was something we had. Then at this particular point, you see that FBC, I can split it into two components, right? This is going to be 4 by 5 FBC. This is going to be 3 by 5 FBC, and so I'm going to have something equal and opposite on this bar here. I'm going to have a 3 by 5 FBC, then I'm going to have a 4 by 5 FBC, equal and opposite to what I have drawn on the bar BC here. So this is going to be 4 by 5 FBC. So they are always equal and opposite. Look at this here. This is 4 by 5 FBC pointing this way. This is 4 by 5 FBC pointing that way. This is on the point B on that particular bar. This is on the point B on the bar BC. They always have to be equal and opposite. This is because of Newton's third law, right? Equal and opposite forces, which means that if I connect these 2 points together, you see that this force will cancel off with this force will cancel off with this force, and obviously there will be no force that will be visibly seen when these two bars are connected to each other. Alright, then I have the applied forces on this bar ABD. I have a force of 200 newtons. I have a couple moment here, 300 Newton meters, and then I had this 106 and 106 newtons. So this is now the free body diagram of the bar ABD, the one that you see on top here, and this is the free body diagram that we're going to be working with. And I want to draw only that free body diagram. Once we have understood that okay, these two forces are equal and opposite, I want to draw only that free body diagram, dimension that, and then employ equations of equilibrium. Alright, so start off by looking at free body diagram of ABD only. So here is the bar ABD. I have a series of forces at the point A, AX and AY, completely arbitrary directions. AY, AX. Then at this particular point, I have equal and opposite forces drawn. This was 3 by 5 FBC from the previous page. This was 4/5 FBC from the previous page. Then I have a 106.1 newtons here, 106.1 newtons there. Then I have this 200 Newton force, and then I have a couple moment of 300 Newton meters, and then importantly I have dimensions for this. So from the point A onwards on to these points here, this is going to be 2 meters, this is going to be 2 meters, and then the last bit of this is also going to be 2 meters. Alright, so now we are ready to perform the force balance on the bar ABD. And to perform the force balance, let us start by summing moments about a particular point. You see, my rationale for summing moments is this. If I start summing forces in the x direction, I have AX as an unknown, 4/5 FBC is also an unknown, I have two unknowns, only one equation. I can't solve for any of them. If I start summing forces in the y direction, I have an AY, I have a 3/5 FBC, I have two unknowns, one equation, I don't have anywhere to go. If I do the sum of the moments about a particular point, if I actually choose the point A, then you see that I'm going to have a moment due to the 3/5 FBC force only, along with the applied forces of course, and then you see that I can solve for FBC. Once I solve for FBC, then I can find AX and AY. Alright, so I'm going to sum moments about the point A clockwise moments are treated as positive. When I do that, the pride of place goes to the couple moment, 300 Newton meters. So this is going to be minus 300 Newton meters first of all. Then the 106.1 horizontal is not going to cause a moment about the point A. The 106.1 vertical is going to cause a clockwise rotation about the point A by a distance of 2 meters. So this is 106.1 times 2. Then I'm going to have the 200 Newton force, 200 Newton all the way to the point A as a distance of 6 meters, once more clockwise rotation. So this is going to be minus 200 times 6. And then you see the 4/5 FBC has a line of action passing through the point A, so that does not cause a moment. 3/5 FBC, right hand rule, curl your fingers, palm faces the point A, counterclockwise rotation. So this is going to be 3/5 FBC times a distance of 2 plus 2, 4 meters. All of this put together is equal to 0. I can solve for FBC. FBC will be approximately 713.4 newtons once I solve for this force. Once I have that, then the rest of it is easy. All I have to do is sum forces in x and y directions. So sum of forces along the x direction, forces pointing to the right, are equal to 0. I have AX, then I have 106.1, and I also have the 4/5 FBC. All of these will be equal to 0. FBC is 713.4. Solve for AX. AX will end up being a negative number, approximately minus 677 newtons. And then sum of forces along the y direction is equal to 0. If I sum forces along the y, I'm going to have an AY minus 106.1. I'm going to have a plus 3/5 FBC minus a 200 is equal to 0. FBC is a pretty large value, so that's going to be trumping the 200 and the 106.1 Newton forces, which means that AY will also end up being negative, approximately 122 newtons. Which means that the support reactions at the point A are going to be AX minus 677 newtons, AY is minus 122 newtons. The negatives here are perfectly fine because at the beginning of the problem we did not know what the directions of AX and AY were. We were lucky with the force FBC that we got it to be positive to begin with, but even if this were negative based on the directions that you choose, do not be surprised. Once you find out that FBC is 713.4, then finding CX and CY is fairly straightforward, and we can go back to the figure here for CX and CY. If I look at this force here, you see that CX and CY are nothing but components of the force FBC. CX and BX and CY and BY are the same, and so I can say that CX is equal to BX is equal to 4 by 5 FBC, and this is 3 by 5 FBC, right? And so essentially I can solve for CX and CY. Here are the final answers. If I look at the bar BC, CX, CY, BX, BY, the actual force on this bar is FBC. It was also FBC on this side. The slope triangle was 3, 4 and 5, and as a result BX, which was equal to CX, was 4 by 5 FBC. Once you perform the computation, this was around 713.4 newtons. FBC was 713.4 newtons. So 4/5 FBC will give you around 571, and then BY is equal to CY was 3/5 FBC, and this will give you around 428 newtons. Alright, So the problem was made easy by finding out that okay, the bar BC is a two-force member. If it's a two-force member, there are forces at only 2 points on this body. The forces are equal in magnitude. You see there, FBC is equal to FBC in magnitude. They are opposite in direction. This is pointing this way, this is pointing in the opposite direction, and they share the same line of action. As you can see, they're along the same line. How do you get that line of action? You join the 2 points on which the forces are acting. Once you do that, you can say that okay, according to Newton's law, on the other bar at the point of contact, the forces are equal and opposite, and so I have an equal and opposite set of Bx and By, or 3/5 FBC and 4/5 FBC on the bar ABD, and then we perform equations of equilibrium, force balance and moment balance, and we obtain the final answers. Right, thank you.